Further, now we move on to dispersion of white light through a glass prism. Dispersion is a phenomenon which is observed when you use a triangular prism. It doesn't occur when you use a glass slab because the opposite faces are parallel to each other. But in a prism, the faces are inclined to each other at a certain angle. Therefore, the light which is emerging out from the opposite face splits up into its constituent colors if we are using a white light. The white light, when it passes through a triangular prism, it splits into its constituent colors, and the split colors appear if they are allowed to fall on a screen, on a white screen, then they form a band of colors which is called a rainbow. Also called a rainbow because the topmost color is red and the bottommost color is violet. Vibgyor. Violet, indigo, blue, green, yellow, orange, red. This is a band of 7 colors that appears when the white light splits into its constituent colors is called a spectrum. Now, why does this happen? Why does the white light splits into its constituent colors? White light contains all these colors. In these colors, the wavelength of red light is maximum and the wavelength of violet light is minimum. Like you have seen that when there is a traffic jam or a rush on a road, the bigger vehicles find it difficult to change their lanes or move to the other side. But smaller vehicles can move easily through the traffic. In the same way, the light which is having a larger wavelength bends least, and the light which is having a smaller wavelength bends most. And due to this difference in the wavelengths, there is difference in the bending of all the colors, and when they emerge from the prism, they form a band of colors known as a spectrum. White light passes through a prism, separates into its constituent colors, and they are forming a spectrum here. But if another prism is placed in front of it, inverted, in inverted position, that means the first prism is splitting the white light into its constituent colors, and the second inverted prism is now recombining those split colors, and the white light is emerging from the other end. This is the dispersion and recombination of light. There's a diagram, same diagram in your textbooks, and not less frequently, this question is asked in your board exams. Now, when the light is coming from the sun or the stars, it is traveling through space, and space has nothing, only vacuum is there. But when that light, which is traveling through space, enters the atmosphere, it suffers refraction. Why? Because the refractive index of the atmosphere is slightly higher than that of space, and that effect is known as atmospheric refraction. The most commonly observed effects of atmospheric refraction is the twinkling of stars, the apparent position of star, the early sunrise and the delayed sunset. All these are effects of atmospheric refraction. Mirage. You must have experienced or witnessed this mirage when we are traveling on a straight road on a hot day. We feel that about some distance away, there is water on the road. But when we reach that spot, there is no water actually. That is also the effect of atmospheric refraction. Twinkling of stars. Why do stars twinkle? Twinkle, twinkle, little stars. Remember that? The light coming from the star enters the atmosphere, and due to the difference in the refractive indices of the vacuum and the atmosphere, the light bends, but different layers of atmosphere have different densities. So each subsequent layer, which is below the above layer, will be having a density slightly higher than the above layer. So subsequently, the light follows a curved path. When it reaches the eyes of the observer, the brain perceives that light is coming in a straight line, and we see the position of the sun here. But actually, the sun is not here, but actually it's here. This change in the position of the sun is due to the atmospheric refraction. This twinkling of stars is also known as scintillation. Stars are very, very far from our Earth. So, a light which is coming from the star is actually considered a single ray of light. That ray of light enters, follows a curved path, and reaches our eye, and we see the star. But the conditions in the atmosphere are not stationary. The air may move, wind may blow, temperature may rise or fall, and due to these factors, that there may be change in the densities of the layers. So, due to changing atmospheric conditions, the angle at which the refraction is occurring, it also changes. And this change causes a flickering in the light, in the ray of light that is coming from the star, and we see that the star is twinkling. But we have been also told that planets do not twinkle. Why? Planets are very, very close to our Earth as compared to stars. So, the light that is coming from a planet is not a single ray, but a collection of rays. Same situation will be faced by those rays also, but actually, quite a few rays are coming from the planet. So, the scintillating effect of few rays is compensated by the others, and we receive a steady light coming from a planet, and that's why the planets do not twinkle. Advanced sunrise and delayed sunset. It's interesting to note that the actual day that we are seeing every day is actually 4 minutes longer than the actual day. The apparent length of the day that we observe is actually 4 minutes longer than the actual sunrise and sunset. We see the sun 2 minutes before it rises above the horizon, and we keep on seeing the sun 2 minutes after it has gone below the horizon. That means we see the sunrise 2 minutes earlier than the actual sunrise, and we see the sunset 2 minutes later than the actual sunset. So, there is an increase in the length of the day by 4 minutes. Why does it happen? When the sun is below the horizon, sun is below the horizon, the light is traveling, enters the atmosphere, and at each layer of the atmosphere, the light keeps on bending and follows a curved path. So, sun is actually below the horizon, but its light is reaching to us, and we are seeing it, we are able to see it. That's why we see a sunrise 2 minutes earlier. And what about the sunset? The sun has set. Sun has gone below the horizon. But the light coming from the sun after entering the atmosphere follows a curved path due to atmospheric refraction, and we are able to see it. That's why even when the sun is below the horizon, we are able to see the sunlight, and that's why we see the sunlight even 2 minutes after it has gone below horizon. So this is the concept of advanced sunrise and delayed sunset. Now, another effect that is created by the atmosphere, not related to refraction, but it is actually the scattering of white light. The scattering of light. Now, what is scattering of light? Or we are familiar with the term Tyndall's effect. Tyndall's effect says that the light, when it passes through a medium like water or air, it gets reflected by the tiny particles suspended in the medium, in air or in water. Those tiny particles are so tiny that we are actually not able to see, but they are large enough so to reflect the light. They are large enough to reflect the light which is falling on them. And when the reflected light, reflected by those tiny particles, reach our eyes, we are able to see from where the light is coming, and we see that the light, the path of the light is visible through the medium. Like when we are sitting in a dark room and the light is entering through a hole or through a slightly drawn curtain, we see the light is coming in a particular manner, in a particular angle, in a particular direction. How we are able to see it? Because when the light is passing through the air, it is also falling on the dust particles suspended in the air, and the light reflected by those dust particles reach our eye, and we are able to perceive that this is the path that the light is taking. So when the path of the light is visible through a medium, due to the scattering of light by the suspended particles in the medium, it is called Tyndall effect, and this gives rise to an interesting phenomenon, that why the sky is blue. Blue sky. Blue sky is not actually blue. When we go into the outer space, we see that sky is black. But when we are at the earth, we see that the sky is blue. Why does it happen? We know that light consists of 7 colors. Each color has its characteristic wavelength. When the light enters the atmosphere, it encounters certain suspended particles which are very, very tiny. So tiny that we are not able to see with unaided eyes. We have to look through a microscope to see those particles. But as compared to the wavelength of light, these particles are big enough to reflect it. But light is composed of 7 colors, in which the red color has the maximum wavelength and the violet color has the minimum wavelength. So those particles scatter the light of shorter wavelengths, blue, violet, indigo, and some portions of green. Those wavelengths of light get scattered, and the longer wavelength, yellow, orange, red, and some portions of green, they are able to reach our eyes. We are able to perceive those colors or see those colors. So when we are looking at the sun in the noon, the sun appears slightly yellowish, is not white. But if we go to outer space and see the images of the sun taken by the satellites, the sun is white, but it is appearing yellow in the noon. Why? Because the colors of shorter wavelength, They are not reaching our eyes directly because they are getting scattered from the particles suspended in the atmosphere. So if we are not looking directly at the sun, we are looking either on either side of the sun, we see what light? The light which is scattered by those particles, and those portions, those wavelengths of light, they together make the sky blue. It is a characteristic color, sky blue color. It is called so because all the wavelengths that are scattered by the suspended particles, when they reach our eyes, we perceive a particular color of the sky, that is blue. That's why sky is blue. So sky is blue mainly due to scattering of shorter wavelengths of light by the particles suspended in the atmosphere. And when we look at the sky, we see that scattered light, and we perceive the sky as blue. When we look at the sun in the morning and the evening, the color of sun is reddish orange, but at the time of noon, it is yellowish white. Why? Again, the answer is found in the scattering of light. When the sun is at the horizon, either in the morning or in the evening, the rays of the sun have to follow quite a long path through the atmosphere. And the longer the path, more is the scattering of light. So when the light rays cover a longer path through the atmosphere, most of the colors get scattered and only yellow, orange, and red reach our eyes. What happens in the noon? In the noon, the light is coming vertically down. It is traveling a much smaller length through the atmosphere. And if the path traveled through the atmosphere is less, scattering will be less, and only very short wavelengths will be scattered. And most of the wavelengths are reaching our eyes. So, color of sky at the noon is yellowish white. What happens in the evening? Again, the same thing. The light is traveling a very long path. Most of the wavelengths are getting scattered. Again, at the sunset, the color of sun is reddish orange. The reason is scattering of light again. That brings us to the end of the chapter. Thank you very much.